So it's a great pleasure to welcome my ex-boss, great colleague and friend, Professor Jim Gates. Jim is a distinguished professor at the University of Maryland, and for as long as I've known him, he has been incredibly busy. So let me give you just an example. When I was trying to look up his CV to introduce him to this talk, I realized his CV has got 103 pages. So telling you about his life would take an entire hour on its own. So I'm just going to give you some highlights about his life. Jim started his career as a physicist at MIT in the 1970s, where he was an undergraduate and a graduate student. He then went on to Harvard, where he took a junior fellow position, and to Caltech, where he was a research fellow. Between 82 and 84, he was a professor in the math department at MIT, and then went to the University of Maryland, where he has been ever since. In 1998, he became the John Toll Professor of Physics, and in 2002, the director of the Center for String Theory and Particle Theory. He has got several positions let me just look it up. He has got several positions, honorary positions, including at the University of Georgetown. He has got many contributions to science, particularly in string theory. He has wrote one very famous book about supersymmetry called Superspace and 1001 Lessons in Supersymmetry. He has got almost 400 papers on spires, and he's not slowing down ever since. So he has got lots of papers. Whenever he's not busy writing his many papers, he appears on TV shows, in particular TV shows on string theory. So I was very impressed when 2 years ago I was visiting Germany, and he appeared on German TV. So he is kind of internationally known. He was on the NOVA program with Brian Greene. He has got numerous prizes, including the National Medal of Science, the Mende Medal, and he's a member of the National Academy of Science. And with all these achievements, even President Obama got impressed, so he hired him as one of his closest advisors. So let me not continue talking about the life of Jim Gates, because it could take a very long time to summarize this, to tell you more about this. And let me just introduce him to his talk. Let me not take more of his time. His talk is called SUSY Holography, Dimensional Reduction, Information Conservation, and SUSY Quantum Mechanics. And before I forget, Jim, we have got a laser pointer for you. It's yours.
Oh, it's the first time you've been thinking of this. Now, the only question is it green or red? All right.
So this is your microphone.
Okay. Well, first of all, it's nice to be back here at Texas A&M. When the physics department here first hired Michael Duff, Chris Pope, and Ergen Sezgin, shortly after that occurred, I paid several visits here to the campus. So I've been here, I think the last time was maybe 15 or 20 years ago. It's been a long time, but this is not my first visit to a College Station. Hi, Katrin. Haven't seen you in a while. So it's very nice to be back. Obviously, the campus has changed a lot. I was talking with some of our colleagues. Says it's just been changing since the 2000s or so. There have been a lot of changes here on campus. And by the way, is this thing on? Is it? Okay, great. So it's just nice to get back and see all the changes on the campus and in the physics department here. I'm sorry I missed Chris Pope, because I was looking forward to seeing him. I haven't seen Chris in a very long time either, but that's the way life works. Okay, so I've been doing some weird stuff in supersymmetry for the last decade or so. And so I wanted to give a progress report on what we've been up to. And that's what this talk is really about. So first of all, supersymmetry. A lot of people, so I have to talk about physics in front of many different audiences. And so one of the things that, you know, as you talk to people who are not physicists, they say, oh, you know, this whole idea of supersymmetry is passé. They didn't discover it in the first scientific run of the LHC. So why do you folks keep working on that stuff? That's what they often ask about physics. And so one of the things I try to get people to understand is that there are all sorts of motivations about supersymmetry beyond the ones that they see in the popular press. And in particular, one of the things that as I've talked to the general population about, is that they are struck by the fact that if you organize the elementary particles into matter versus force carrier and spin, you get the chart I'm showing you behind me. But if the universe is supersymmetric, it looks like that. The public gets symmetry. And they look at this segment, oh, I get it. It looks much prettier, you know. And so that's a great reason now to switch from not believing in supersymmetry to believing in supersymmetry, right? Well, we know it's a little bit more complicated than that. But in fact, this is really a supersymmetric universe. What I've shown you here, of course, are the particles of the MSSM. If the in MSSM is actually what nature does, and some of us suspect that's likely true for other reasons, mu parameters and stuff like that, then nature will, if she's supersymmetric, be much more symmetrical than the standard model, which is represented by this diagram. Okay, so, but the real reasons I believe in supersymmetry are vastly different even from that. I wrote an article in the British Journal Physics World in October. It's called Sticking with SUSY. And in that article, I talk about why I think ultimately SUSY will show up in nature. By the way, in the second scientific run at the LHC, I give the discovery no more than a 50-50% chance of being there. And so you might think I'm pessimistic, but in fact, I've been doing supersymmetry so long, I remember the entire arc of the field in terms of particle physics. So I remember there was a time when supersymmetry was considered disreputable, and no real physicists worked on it. That changed in the early 80s with the discovery of the MSSM and supersymmetry breaking through supergravity. Then suddenly it became the rage. And I've watched several generations of young people learn about supersymmetry after that transition. And so for that generation, the non-discovery of supersymmetry at the LHC in the first scientific run was an utter disaster because they were convinced that they knew what God's truth was. Now, as you know, the universe doesn't work that way. It's much more complicated, subtle, and for some reasons which I could go into more deeply, I think the supersymmetry is out there for having something to do with quantum fluctuations and controlling them. Because the supersymmetrical theories have some very singular properties when you look at them under normalization. However, let me start getting a little bit more technical. This is a picture of a chiral multiplet. If the supersymmetric universe is true, the supersymmetry is an accurate picture of nature, then this set of mathematical objects, and in particular this one, will be basically half an electron. In order to construct an electron in a supersymmetrical theory, you would have to use two collections of this set of fields. What you see here are basically the transformation laws of supersymmetry. The way to interpret this is that you have these states A, B, psi, F, and G. You have a transformation which you can think of as kind of like a rotation. If you had a rotation, it would rotate X into Y, Y into X. And so in supersymmetry, we rotate between bosons into fermions, and we rotate fermions back into bosons. And in fact, these equations are the so-called Vestamino transformation law for the scalar multiplet. Similar multiplets exist, including the photon. So this is a vector multiplet. It is accompanied by, if this is a photon, that's the photino. And this thing D is called an auxiliary field. And then finally, there's a multiplet that occurs in all closed string theories that describe gravity. They have a dilaton-axion pair. The axion is often described by a pseudoscalar, but in terms of superspace, there are reasons to believe that the natural description of the axion is actually a rank 2 antisymmetric field. And then these are the supersymmetry transformations of fields. So that's supersymmetry in a nutshell. The first one being what Vestamino discovered in 1972 or 73 or so, and the rest of them were discovered subsequently. In the early to middle 2000s, working with a guy named Michael Fox, we discovered that supersymmetry has a graphical representation, that there are a set of graphs that describe supermultiplets with complete fidelity, namely containing all the information that I showed you before when I showed you what the field content was and what the transformations, there are graphs that contain all that information. Now, the way that you get these graphs is kind of peculiar, and I'll talk about that in a minute, but here's an example of such a graph. Here's a system with two bosons, phi1 and phi2. So this is not the scalar multiplet that we would need for the minimal supersymmetric standard model. It's another multiplet. And two fermions, psi1 and psi2. And by the way, we choose a real basis. So the bosons are real, the fermions are Majorana fermions. So this is an example of a supersymmetrical system. Here, you can think of the D's as the Q's in the language that people often use. How about a Q as a supercharge? So these here are the supercharges. And in fact, this set of equations, if you calculate D, the commutators on the D's, you'll find that these produce the usual supersymmetry relationships, that D bracket D is a time derivative. But in fact, this set of equations is contained in this picture like sort of a Feynman diagram. How does it work? Well, each node represents one of the functions. So this is the phi1 function, that's the phi2 function. The dark nodes are the fermions. So that's the psi1, that's the psi2. So now we've covered all the fields that occur over here. And now the links that you see here are the supersymmetry derivative operators. If you think of the supersymmetries as generating translations, and you look at the orbit of those translations, you get these colored diagrams. And so if I take the first supersymmetry, act on phi1, I get psi1. Well, that means here's phi1. Green is the first supersymmetry. It leads to psi1. And so this equation here is encoded by this part of the diagram. In a similar manner, if we take the first supersymmetry and act on the second boson, it leads to the second fermion. Well, that's this link here. If we take the second supersymmetry and act on the first boson, so that's D2 on phi1. Well, here's phi1. D2 is the red link. It leads us to psi2, and that's what we see here. And so these pictures are like Feynman graphs, and they encode the orbits of supersymmetry generators. One other thing is that when we move up, the answers that we get on the right-hand side have no sign derivatives, but you might want to know what the supercharge does on this fermion. So that would be D1 on psi1. Well, D1 on psi1 produces ddt of phi1. Well, phi1 was the green link, but since it goes down, we put a time derivative in. And so it's a very simple graphical way of encoding equations with the property of supersymmetry. It turns out that this diagram is slightly different, but there are these Feynman-like rules that we have found in these things, and if you apply them, you find out that you get a slightly different set of equations. In fact, this looks a whole lot like the chiral multiplet that I showed you we needed for the minimal supersymmetric model. So Michael and I gave these images the name Adinkras because, well, we found them, so, you know, when you find something in physics, you name it. So we just picked this word out of the air, so to speak. We said, well, let's just call these pictures Adinkras. This is what the chiral multiplet looks like, by the way. Not that simplified picture that I showed you before, but the one that, if the universe is supersymmetric. And how do you find this? Well, the way that you do it is you take the field theory version. So let's go back to that. So there's a field theory of the chiral multiplet. And what you do is you imagine taking a line in the forward light cone and reducing the theory on this line so that all the coordinates are proportional to this one 4 vector in the forward light cone. For simplicity's sake, you could choose this 4 vector to lie on the time axis. If you do that, it means all the functions at the end of the day will only depend on time. And so if you carry out that process on this set of equations, you are led to this graph. So these graphs come along with the equations when you make this reduction along the time axis. Now, for those of us who are field theorists, we've seen something like this before. It's like looking at the Wigner-Little group. Because if you start with a field theory and you want to know the Wigner-Little group, what you do is you reduce to the origin and then look at the transformations that are left over. So these are the analogs of that process, but looking at supersymmetry. So the vector multiplet looks like this. The chiral multiplet looks like that. And that tensor multiplet or the axion multiplet looks like that. So when we first made this discovery with Michael, we thought it was really interesting that equations have contain all the information of this light line like reduction of the field theory. And so we began to wonder how much information is there actually contained in these graphs alone. And so we started to explore that. So a little detour. I had been wondering about these ideas since the middle 90s, and I had actually talked with some lots of physicists, and we weren't really making progress. So I started talking to mathematicians. And one of my mathematician colleagues was a guy named Greg Landweber. And in fact, there's a website, which is here, where there's an app that lets you build these graphs. So that if you want to study the mathematical properties of these things, you can actually download this app and begin to study things about topological questions, linking numbers, and things like that. This particular graph is a more complicated version. I showed you the particles for the chiral multiplet and the vector multiplet, which would be the major components of the MSSM. But in fact, if you know something about supersymmetry, you perhaps know that the vector multiplet that I wrote for you earlier is actually part of a bigger multiplet, something called a real scalar multiplet. And that the vector multiplet is that thing in what's called the Wessaneal gauge. Wessaneal gauge is a kind of a truncation. This is the larger object here. Okay, so now we have found these objects. We start asking the question, what are they actually good for? Because this reduction procedure that I showed you can be carried out in any dimension. In fact, that two-color example that I first showed you is actually the result by starting from a two-dimensional version of the chiral multiplet and reducing it along the light axis. So these images that I'm showing you are intrinsically part of any supersymmetrical theory that you want to write. You just have to go look for them. Now, the question is, how much information do these things contain? Well, before I go there, let me point something out. Ultimately, we are going to find that these graphs that I'm showing you all start out as hypercubes in some space. And the thing that's interesting about hypercubes is if someone gives you a hypercube in some space, you can always choose the vertices to lie at points whose coordinates take that form. You just orient it properly, and that describes a hypercube. Now, what's interesting about this is that if you orient the vertices like this, then of course each of these plus or minus 1 can be written as minus 1 to some power, and the power has to be either 0 or 1. But variables that take on values 0 and 1 are called bits. And what that means is that if you start with something that has cubical topology, it automatically has bits at some level built into its mathematical structure. So here's that diagram I showed you before, the big one. And now, in order to build these things, I've actually also told you how to build them. What you do is that you start with a hypercube. So imagine starting a hypercube. A hypercube, well, all the faces of hypercubes are squares. And so what you can do is that on any of the faces of a hypercube, occupy the vertices with these open and closed dots. And since every face of a hypercube is a square, what you'll find is if you start by doing an orientation open, close, that gets inherited on all the faces of the hypercube. The next thing that we do is if you start with a hypercube, and let's think about 3 dimensions for a moment. In 3 dimensions, there will be motion along the x-axis, links along the y-axis, and links along the z-axis. Let's color all the links that are parallel to the x-axis. Let's color them red. Let's color all the links that are parallel to the y-axis blue, and let's color all the links parallel to the z-axis, say, green. Then what you will have done is taken the hypercube, you will have dressed up the nodes, open and closed nodes, and then all parallel lines will have the same color. And now finally, we put one more rule in place. We say that as you traverse any square face of a hypercube, you want an odd number of dashed lines to show. Now this odd number of dashed lines is kind of curious, but what it actually does is impose the supersymmetry algebra on this Feynman-like graph that I showed you before. That's actually what puts the supersymmetry algebra there.
So supersymmetry can be, instead of thinking about supersymmetry as a construct that comes from field theory, we can approach this purely from an algebraic, a topological approach. Start off with hypercubes, all parallel lines the same colors, alternately dress the vertices, open and close nodes, and then demand that every square face have an odd number of dashed lines. This odd number of dashed lines, by the way, is non-trivial, because if you actually try to do this construction, you might run into you might run into an obstruction. That is, you might find that when you put an odd number on a certain number of faces, when you try to close it, it would be impossible to do. Now, when we first made this observation, we didn't know whether you could always impose this rule or not. And this is what mathematicians are good for, because they can solve such problems. And it turns out that this odd dashing rule, I was talking to a graduate student at MIT by the name of Yan Zhang. He recast this as a problem in combinatorics and constructed a proof that the odd dashing rule can always be solved. And so, in fact, just on the basis of combinatorics, we now know how to construct supersymmetry representations without any reference at all to field theory. We have an entirely different way to think about what's the origin of supersymmetry. It has to do with what my mathematicians call decorated cubical cohomology. Totally different way to think about supersymmetry. Now, my claim is I can build arbitrarily large supersymmetrical representations because I know how to build arbitrarily large hypercubes. And with these rules about dashing and coloring, I just keep applying them over and over, and I can get supersymmetry representations. Now, that's okay, but the question is, can I get irreducible supersymmetry representations? Because this is an irreducible supersymmetry representation. And if you think about it, you should challenge me. Because you see, that has there are four different colors of links in that diagram. Something that had four different colored links means that there had to be four orthogonal directions. But a hypercube in a space of four directions should have 16 vertices. There are only 8 there, 4 open and 4 closed. So how in the world is this thing a hypercube? Well, the answer turns out to lead us to a weird discovery. By the way, this is the hypercube that I'm talking about. The color, you can see 4 colors. It's got 16 vertices, just as I told you. Say again? So every open node is a boson. So in this picture, there's one boson here, call it B1, B2, B3, B4, B5, B6, B7, B8. So there are 8 bosons in this multiplet, and each closed node is a fermion. So psi 1, psi 2, psi 3, psi 4, 5, 6, 7, 8. Right? So this is a system with 8 bosonic functions and 8 fermionic functions. And now, this thing, by the way, really is a hypercube in 4 dimensions. So just like you can take a cube and project to the 2-plane, you can take a 4-dimensional hypercube and project to the 2-plane, and this is what it looks like. This is also called a Hasse diagram in some crystallographic applications. So now remember, we're talking about topology, cohomology, but not necessarily field theory. And so we want to next understand irreducibility. So this is that hypercube again. This time I've taken away the dashings. But this is not the chiral multiplet, because the chiral multiplet only had 4 open nodes and 4 closed nodes. It's also not the vector multiplet, because the vector multiplet had 4 open nodes and 4 closed nodes. It's also not the tensor multiplet, because it also had 4 open and 4 closed. So the question then becomes, how does this thing, which has 8 open and 8 closed, how is it related to these irreducible representations? And the answer turns out to be error-corrected codes. You see, the function at the bottom I can name in many different ways, but let me choose to name it as 0, 0, 0, 0. And then if a fermion is connected by a red link, what I will do is change the first 0 into 1. If it's connected by the green link, I will change the second 0 into a 1. If it's connected by a blue link, I will change the third 0. And if it's connected by a black link, I will change the fourth 0 into 1. Now, That means, for example, if I started with this function here and apply the supersymmetry generator, remember each color is a different supersymmetry charge. So if I apply the supersymmetry charge red and green, start with this node, do red and then green, I wind up here. Because I would have to use a red node to get to here and then a green link to get to there. However, there's another way to use green and red. Do green first and then red, and I get to the same place. And so these names that we're using are telling us how many color links. If you think of the bottom link as a reference link, the names of everybody else is related to the number of colors that you need to get to them. And so to get to the top, you have to use one red, one black, one green, and one blue, and that's why this top node is named 1, 1, 1, 1. Now, so every cube, this is something you can do for every cube no matter what the dimension is. You can pick one as a reference node, and then figure out the names of everybody else by the colors of the links. Now, the next thing to observe is this thing is twice as large as the irreducible representations I showed you. So let me reduce it. I'm going to give you a prescription for reducing it. The prescription is that when you join, I'm going to, well, one way to say it is we're doing something like an orbifold. And the way the orbifolding works is that if a function, so start with a function like this, we will identify this function with any other function that differs from it by being its complement. Now, since this is 0, 0, 0, its complement is 1, 1, 1, 1. So when we do the orbifolding, we identify this function with that function. We would identify this function with that function because that's its complement. We would identify this function with that function because that's its complement. And in this way, you can go from something that has 8 open and 8 closed to something that has 4 open and 4 closed. And when you do that, it takes you back to the chiral multiplet. And so the chiral multiplet is a hypercube where you do this orbifolding of identifying the complement nodes with respect to these names in terms of bits. Now, 1, 1, 1, 1 turns out to be a rather interesting bit because every day, all of you use computers. Even someone right now is using a computer. You use computers every day. And you're used to reliably sending information back and forth. And yet, in the real world, the transmission of data is never perfect. That means that some of the ones that you create might be zeros when they get to the other device. So the zeros you create might be ones on the other side. So this is a problem that a computer scientist by the name of Richard Hamming started thinking about in the 40s, at the end of the 40s. And he found a solution. His solution is implemented when you use computer technology every day. What happens is, as you create your bits, your ones and zeros, your computer puts extra ones and zeros into the message. And then it is the totality of these ones and zeros that are sent to a receiver. Now, the ones and zeros that the computer puts in are put in a very special way. They're put in such a way that when the second computer reads them, it can tell when bits were flipped. And therefore undo the flipping and get a reliable transmission of data. And you use this every day. These extra code numbers that you put in, that's what an error correcting code is about. The Hamming code is an example of an error correcting code. The numbers 1, 1, 1, 1 are the simplest example of what are called block linear error correcting codes. The largest member of that family is something called the checksum Hamming code. I think it's 32 bits long as opposed to simple 4 bits. So there are lots of error correcting codes that are known to computer scientists. This family is just one of them. But what I've just told you is that this family actually defines irreducibility if you think of this cohomological way of the origin of supersymmetry. So the error correcting codes are intrinsically part of how you define irreducible representations. So that result was so odd that, and now let me talk about my collaboration, because this work has been done principally and mostly in collaboration with Tristan Huch, Michael Fox, Kevin Iga, Charles Duran, and Greg Landwehr. The latter three are mathematicians. So this is our interdisciplinary math physics conversation group. When we first spun this result, that error correcting codes are embedded in the structure of supersymmetry, if you think about their origin in terms of cohomology, We wrote a paper about this, and we submitted it for publication, and it was rejected. We made a few changes, because those of us who are authors, rejection is kind of the coin of the realm. Happens all the time. You try to change the paper to answer the questions that the referee asked, and we did that, and the paper got rejected again. So finally, we just gave up publishing it. And but we knew the result was correct. The problem was that we couldn't get our referees to understand what these error-correcting codes were in this context. Particle physicists don't normally talk about error-correcting codes unless they're DAQ people, data acquisition folks. They know about error-correcting codes. But those of us who are formal field theorists, no one's ever taught us about error-correcting codes. And so we couldn't bridge the communication gap with our referee, even though the result was stunning. Now, at this stage, the other thing I have to tell you is that this result has gotten me into more trouble than anything I've ever done in my physics career. Because I made a joke about it. The joke went as follows. I don't know if you've ever seen the science fiction movie The Matrix, but The Matrix is a movie where there are creatures like us in a world that's kind of like our world, but the entire construct is a simulation. It's a virtual reality. And so I made a joke. I said, but imagine that there were some physicists in the movie The Matrix. How might they discover that they live in a virtual reality? Well, one way might be if they saw signs of computer code in the laws of their physics. Some person got the joke. But I'm telling you, if you think about supersymmetry in terms of this cubical cohomology, well, first of all, you have to wonder whether supersymmetry is an accurate description of nature. Let's for the moment assume it is. If supersymmetry is an accurate description of nature, we can't avoid these error-correcting codes. And so there are people, there's a site at YouTube where some young man who I've never met got hold of this result, and if you go to the site, you'll see it basically says, Jim Gates has discovered we all live in the Matrix. Now, Jim Gates doesn't say that, nor does Jim Gates believe it, but this website has been viewed by over 500,000 people. And so this meme keeps propagating itself, and I keep getting email from people I've never heard of before, asking all sorts of outlandish questions about, some of the really weird ones is, thank you, thank you, thank you. I always knew we lived in the Matrix. But what I think is actually something different. And at the end of the talk, if someone reminds me, I'll tell you what I think this means. I don't think we live in the Matrix. Okay. So now I have introduced you to this idea that we can look at supersymmetry without looking at field theory. We can look at supersymmetry in terms of cohomology, error-correcting codes, and these things that have the topologies of cubes. Because that's the important thing, that the topology is that of a cube in terms of the decorations. So so this is a chiral multiplet, but not quite. This is a chiral multiplet where I've taken the original auxiliary fields, and that's what we call F and G, and every place they appear in the transformation laws, I've actually replaced them by the time derivatives of F and G. If you do that, you find out something rather interesting, that A and B, which are the squarks, if we're talking about the minimal supersymmetric standard model, you find out that A and B, in fact, enter these equations in a manner that is rather symmetrical with F and G, which are what we normally call the auxiliary fields. And so this is rather, and in fact, you can even look at the transformation law for the fermions. You'll see that every boson in this transformation law appears with the dd tau. That's because we've done the replacement. That means that there's some kind of a democracy that suddenly appears. Namely that auxiliary fields, which we normally, in 4 dimensions, we think of auxiliary fields as being rather trivial and not being dynamical entities. When we do this light cone reduction and then do this redefinition, auxiliary field bosons and physical bosons are almost indistinguishable. They enter the equations in the same general manner. That's true for the vector multiplet. It's also true for the tensor multiplet. You don't even have to make any changes because the tensor multiplet already had this form. If you draw a picture of these things where you use the time derivatives, the graphs change because the heights in these graphs correspond to the engineering dimensions of the fields. When you take a field and replace it by a time derivative of itself, that effectively takes a node and lowers it in the graph. And so this is a graph of the chiral multiplet after we have lowered the F and G fields. This is the vector multiplet after we have lowered the D field. That's the tensor multiplet, for which no lowering was required. Now, if you look at all three of those pictures, they look essentially alike. They all look alike. And so the question is, if someone just gave you those graphs, how do you use that information to figure out one corresponds to a vector multiplet, another one corresponds to the tensor multiplet, and the third one corresponds to the chiral fanatic multiplet? What information in the graph tells you that? Well, just a moment. I think I have a slight problem here. Hang on a second. I think I do. Right now. Let me back up a little bit so I'll talk about this construction process a little bit too. Make sure everyone's on the same page. Here's a square. I want to turn it into one of these graphs that contains a supersymmetric multiplet. Dress up each vertex, as I said, open, close, on every square face. All parallel lines get the same color. An odd number of dashing on any square face. And the third rule is that no open node and closed node can appear at the same altitude. You can get out of that by doing this. And these are the two graphs that we saw earlier. So these two different supersymmetry representations are born as squares in this language. You can do it. So this is the hypercube. What I've done here is I've taken the cube in 4 dimensions. I've looked at its projection to the 2 plane. I've done the dressing. Here you can explicitly see the dressing on each of the square faces. So open, close, and then every parallel line gets the same color. And then you ask as though this is a real point that you can hang, and you get that. And that's the figure that we kept saying was the 16 open, 16 close. It started as a cube. We did the bits. And now this irreducibility, I told you, this node joins with that node. This node is to be identified with that node by some orbifolding-like process. And this one is that. This one combines with that one. Always total sum 1, 1, 1, 1. That's the error correcting code. So it turns out that there's another way to combine supersymmetric multiplets. It's illustrated here. You start with 2 of these 16, 16 nodes. And then what you do is you take linear combinations of the variables in the middle, these things we call x's, you set them equal to linear combinations on the right. And what's odd about this is that only certain linear combinations will preserve the supersymmetry algebra. And in particular, the only combinations that preserve it are where you take x1 plus x13 plus x24, you set it equal to y12 minus y34. And what's distinctive here is you'll notice that the numbers that you get here, 1, 2, 3, 4, those in fact, if we convert back into the language of nodes, these are adding up to that 1, 1, 1, 1 combination. So we believe that all irreducible representations must have this 1, 1, 1, 1 error correcting code to define the irreducible representation. And this thing here, by the way, is very different from a chiral multiplet. It is an irreducible representation, but in terms of graph theory, it looks like this monster. You have to be someone who isn't supersymmetry, but this is what's called a complex linear multiplet. It's a 12-12 representation of supersymmetry that's not often used, but we've known about its existence for very long time. To get it, you need an error correcting code. That's the basic message. That even though you didn't do a folding, an orbifolding, in order to combine the two objects to get an irreducible representation, error correcting codes enter. And so this is our strongest evidence that error correcting codes enter every irreducible representation. So I use the word information loss in my title. So let me talk about that for a moment. Again, I want you to imagine you're an ordinary field theorist, and you start talking about the Klein-Gordon Lagrangian, a massless Klein-Gordon field. In fact, let's talk about 3 of them. It looks like that. This index I takes some values 1, 2, and 3. And now we do this reduction on the light line I talked about. This action can be reduced, and afterwards it looks like that. Now let's take Maxwell theory. Again, first go to Coulomb gauge, so we get rid of A0, and then do the light line reduction on the variables. And do that, you get this. Now look at these two expressions. This is what comes from Maxwell theory. This is what comes from Master's Klein-Gordon theory. Those two expressions, except for names, are the same. If you change the A's in one to 5's in the other, they're exactly the same result. This is an example of what I refer to as information loss, by the way. If you started with the higher dimensional theory, that is 3 spin 0, massive spin zeros, do the light reduction, or start from the Maxwell theory, do the light reduction, the results that you get for ordinary theories are indistinguishable. You have lost the information about the spin of the particle in the higher dimension. The two Lagranges look the same. That's what I meant by information loss in the title. That under ordinary reduction, non-supersymmetric reduction, information is lost when you reduce a field theory. My claim is that that's not true if it's a supersymmetrical theory. Because these pictures that I showed you, so this is actually the chiral multiplet, that's the vector multiplet, and that's the tensor multiplet. These pictures, because they contain more than just the fields in the theory, they also contain the supersymmetry transformation laws. The supersymmetry transformation laws secretly know about the spin of the particle. And so the information that was lost in the non-supersymmetrical theory is recoverable in a supersymmetrical theory because the transformation laws retain that information. And so the information, that means that supersymmetry compactification is information conserving in a way that ordinary compactification is not. Now, how do you extract this information? Yes, sir. Yes, I did. The answer is no, I won't. So the fixing of the gauge, let me see. You can think of that as an extra prescription that we put on this kind of construction, namely, start with some higher dimensional gauge theory, I don't care what it is, and then demand that any field that has a 0 index, we set it to 0 at the very beginning. You can think of that as a kind of a gauge fixing condition. No matter. Right, exactly. Well, these pictures, well, I remind you, Hamiltonian formulations typically are not gauge invariant. Yes, I know, but the point is that these things work like Hamiltonians in terms of the utility of these things in trying to understand how the supersymmetry. Right, I did gauge fixing. Right, I did gauge fixing and reduction. Without the gauge fixing, without the gauge fixing, what actually happens is that you find out that this graphical construct, that the resulting theories do not sit in the space of theories that you construct in these cubes. So the gauge fixing was actually implicit in the fact that I said, I want to find these representations and map them onto the space of cubical cohomologies. If you were trying to use this to actually construct some kind of dynamical theory, the first thing is you would try to construct essentially something that looks like a Hamiltonian. Then you would later have to ungauge fix that to go back to a fully covariant theory. That's correct. So these matrices, by the way, these images that I showed you, these diagrams, if you talk to someone in network theory, they might say, well, gee whiz, we know about these things. If in network theory, there's a notion of what's called an adjacency matrix. And since Wikipedia is the font of all wisdom, I simply went to the Wikipedia, as you can see, and looked up the word adjacency matrix. And what you find if you do that is that these pictures I've shown you of the orbits of the supersymmetry generators also describe the links of a network. And that's what adjacency matrices are for. They're classically defined to be if two nodes are connected by a link, you put a 1 in that entry in the adjacency matrix. If there's no connection, you put a 0. So that's the 1s and 0s. We've made it a little bit fancier because we looked at different equivalence classes. That's our coloring. And then we've made it even more fancy because we're allowed to put plus and minus signs in. But these things, if you take the absolute values of these matrices, they are adjacency matrices for these diagrams that I've been showing you. So it turns out that if you think about these things in terms of adjacency matrices, and these L's and R's, by the way, are the adjacency matrices that you get from the diagrams, and what you find out is that the adjacency matrices themselves actually satisfy an algebra. Now, when I first showed this to people who work in network theory, they were surprised because apparently this example of adjacency matrices that then on top of that are a representation of algebras apparently not so common. Now, the algebra they satisfy is really interesting. So these are basically associated with the transformations of bosons to fermions. These are associated with the transformations of fermions back into bosons. That's how you define these objects. If you put them in this off-diagonal structure, you find out this thing gamma, just in terms of the pictures I showed you, leads to a Clifford algebra in the color space of the orbits of the generators. This is not the Clifford algebra of spacetime, by the way, because this, after all, is a Kronecker delta here, not the Minkowski metric. So, as I said, the L's are associated with transformations of bosons and fermions. The R's are associated with transformations of fermions back into bosons. And if you actually do a little bit of algebra, you find out these conditions right in the middle are exactly what you need to conclude that phi and psi form a supersymmetric multiplet, that the D algebra is satisfied in the normal way. Now, what about this business of I know how to tell this, I have retained the spin information? Well, these L matrices you can break up into permutations times factors of plus and minus 1 on a diagonal. We call these things Boolean factors. We have a nice way of naming them here, but every L matrix has this form. And if you do this and break them up into permutations times the sign factors, what you can show is, first of all, for the chiral multiplet, you get this set of things here. Here you can see the sign factors denoted by this notation. This is just a way to tell me the numbers of plus and minus signs in the diagonal. Here's the actual so-called cycle notation for permutations. I don't know if you've ever worked with permutations, but it's a standard tool for talking about permutations. And now I want to show you something rather interesting. Look at the permutations that occur here. These are the permutations associated with the chiral multiplet. Look at the permutations that occur here. These are the permutations associated with the tensor multiplet. And if you actually look at the permutations, you see 2, 3, 4 here, see 2, 3, 4 there, 1, 4, 3 here, 1, 4, 3 there, 1, 2, 4 here, 1, 2, 4 there, 1, 3, 2 here, 1, 3, 2 there, and furthermore, 2, 4, 3, 2, 4, 3. In fact, there's a matching, except that where there are L's in one place, they are R's in the other. Now, I was working with one of my graduate students when we first made this discovery, and he was totally puzzled when he got this result. But I immediately knew what was going on. So what's the relationship between a chiral multiplet and a tensor multiplet? I'll just use the blackboard over here. Chiral multiplet is just scalar pseudoscalar. Tensor multiplet, also called linear multiplet, also called axiom multiplet, is scalar skew symmetric second rank tensor. If you're a field theorist, you know something about a relationship between these two things. They're connected by what we call Hodge duality. That is, in this theory, you have this pseudoscalar. It has a field strength, which I'll call curly F mu, which is nothing but its first derivative. The Lagrangian for this thing is actually the square of this thing. It's just d mu d mu. On the other hand, so we have this thing F, and the equation of motion, E-O-M, equation of motion is just this. Because it was a massless scalar. In terms of this variable, this is the massless, this is the Klein-Gordon action. This definition of F, on the other hand, multiplies that. Because since f is a derivative of something, you plug it in here, it vanishes. So this is the chiral multiplet. Looks like that. Let's go to the tensor multiplet. What's the kinetic energy operator for the skew-symmetric tensor? Well, it turns out to be an object that you can write as epsilon mu nu, rho sigma tau, d rho d sigma tau. So I'm going to call this thing H. That, if you try to write a Lagrangian is the square of this thing. You'll notice because of the definition of H, d mu of H equals 0 because of the epsilon tensor that's in there. On the other hand, if you wrote the Lagrangian, that's the square of this thing, and then vary with respect to B, that will give you an equation of motion. The equation of motion that you get, so put EOM here. The equation of motion that you get for this thing H is this. And now if you look at the totality of this and that, and compare it against this and that, you realize the totality is exactly the same. The only difference is what you call the equation of motion. In one case, this thing was the equation of motion for a ordinary spin zero scalar. In the other case, this thing is the equation of motion for a skew-symmetric tensor. This is Hodge duality. This is precisely the meaning of Hodge duality. And so the chiral multiplet and the tensor multiplet are connected to each other by Hodge duality in space-time. But that is why these two sets of matrices are exactly the same but reversing each other. In other words, what I've tried to convince you of is that in a theory with only a time dimension, with only a temporal dimension, if it's supersymmetric, I can see Hodge duality being realized. And that's kind of interesting and surprising, because ordinarily you would say, if I'm in one dimension, there's no such notion as Hodge duality. But because I can look at the properties of these graphs, I can see Hodge duality. Now, you might not be convinced that that's Hodge duality, so let me try to give you another argument. Look at the vector multiplet. It's sitting here. And now let's again do this decomposition into sign factors times permutations. You'll notice that for the transformations for boson that goes to fermions, we see a 1, 2, 4, 3 here, a 2, 3, a 1, 4, and a 1, 3, 4, 2. Now let's look at fermion into boson. You see a 1, 3, 4, 2, but that's the same thing as this. You see a 2, 3, well, there it is. There's a 1, 4, and there's a 1, 2, 4, 3, but that's the same thing as that. And now stop and ask yourself a question. How does a spin 1 field behave under Hodge duality? It transforms into itself. A spin 1 field, and we can do that in this same language. This down. So let's do the spin 1 case. So in the spin 1 case, we start off with something like the photon. Its field string is the curl of A. The Lagrangian is the square of this thing. So the equation of motion looks like this. However, because of this definition, you also have that epsilon mu alpha beta d rho f alpha beta equals 0. And we normally call this the Bianchi identity. But if you did a Hodge duality transformation on this thing, you would change Bianchi identity with the equation of motion. If you tried to solve it, you would find that you would again have a vector. That's Hodge duality. And that's why the same set of matrices show here. So in other words, I can be in one dimension and I can identify a vector. I just look at the permutation part of the transformation laws and ask, do I see something different or the same in the totality of them? If they're the same, it's a vector multiplet. So we can see properties of spin In 4 dimensions, we can see it as one-dimensional quantum mechanical behavior. Let me skip that. Now, this may seem strange to you. How can it possibly be that in 1 dimension, a theory that only depends on time, how can it possibly be that I can see spin from 4 dimensions? Because spin, we normally think about you have to have spinors or vectors or something that carries a non-trivial representation of the Lorentz group. Well, the way that it can possibly be is because when we look at these supercharges, these diagrams had 4 colors. That means there are 4 supercharges. And in fact, there's an automorphism group that acts on these supercharges, which is precisely SO4. Now, if you know something about SO4, you know SO4 can be decomposed into SU2 cross SU2. And so, if you start with SO4, and these are, in fact, representations of SO4, they, in fact, split precisely into 2 commuting factors of SU2. And so the fact that this thing carries the automorphism group of SO4 means that it will necessarily carry representations of these matrices. But if someone gives me these 2 SU2s that sit within SO4, I can use them to construct gamma matrices. And so there's this peculiar relationship between SO13 and SO4 that you can actually use in the context of these models to say, yes, I'm seeing spin. And then, by the way, in particle physics, we talk about spin from isospin. That's what's going on here. We're looking at a behavior of spin from isospin, just as people started talking about as early as the mid-70s and early 80s. So you can see spin in 1 dimension by looking at the properties of the network. Let me talk about another discovery. So we have now these 2 very different views of supersymmetry. On the one hand, we have supersymmetry by starting from 4-dimensional field theories and looking for multiplets that satisfy the supersymmetry algebra. And now I've given you a definition of supersymmetry that doesn't know anything about 4 dimensions. It starts from cubes. It uses error-correcting codes to find irreducible representations. You look at the length. You look at the permutations inside the matrices, and that will tell you about whether things are either scalars or tensors or vectors. But this is all 1-dimensional information. Suppose you start only with 1 dimension, because I've been kind of cheating these folks so far. I've been starting with the higher dimensions. I've been doing the reduction, and then I find these objects, and I say, aha, look at the funny properties of these objects. But you could just say, wait a minute, Professor, it's like a swindle. Because you started from 4 dimensions. So now let me tell you that I haven't swindled you. And the way to know I haven't swindled you is to actually do 2 parallel sets of calculations. The first set of calculations is stay up in your 4 dimensions. Stay up there. I don't care if you come down. Just stay up in 4 dimensions. And now, do this calculation of the commutator of 2 supercharges on any fermion in your theory. You'll find if the theories of Valise, as we talked about, well, you can start with 4 dimension and reduce Valise. You're going to get some numerical tensor. You do a boson, you're also going to get some numerical tensor. So we call these tensors Holoraumy tensors. And I have to beg forgiveness to both Katrin and Melanie because the Raumy part, of course, we recognize as the German for space. And, of course, the hollow part is, of course, Greek for whole. So we're mixing 2 very different linguistic traditions and putting this word together. But we do mean this as the whole space. So even though we've broken some linguistic rules here, we have a concept that you can calculate. And that's the important thing. Someone gives you a multiplet, you calculate it. Now, do this set of calculations starting in 4 dimensions, come down to 1, but don't do anything about the cubes. Don't introduce any cubes at all. Just do the calculation. If you do that, for the chiral multiplet, you get this. It's now only SO3 symmetric because you did the reduction. For the vector multiplet, you get this. And you can also do tensor in the other examples here, too. You just do the calculations. Don't cheat. Just do the calculations. Forget about the cubes. And now, I come along and say, okay, I'm going to give you some data now on cubes. I'm going to ask you to do a calculation. The calculation on the cubes is not a calculation with D algebras. It's a matrix calculation. Namely, I want you to do this. Take these L and R matrices. Just basically calculate these linear combinations. You're going to get some matrices. These matrices, in principle, are different from the ones you get from 4 dimensions. But now, if you actually calculate these things, you can form a trace of these objects for different multiplets. So this R prime label is a representation of whether it's vector multiplet, chiral multiplet, multiplet. If you do it on the 3 here, you get this matrix. If you go back to the 4-dimensional calculation and work in terms of the gamma matrix construct, you get this matrix. But these two matrices are exactly the same. And this is what I meant by holography in the title. That you can take the data purely from the point of view of the cubes, calculate something, and then there's a set of calculations that you can do in 4 dimensions and compare the 2 calculations and see when they match. That's basically what we mean by correspondence. This is strong evidence that this cubical-based view of supersymmetry actually does know the information about what's coming from the field theory. Because essentially what you're doing is calculating a metric on each space and then comparing that metric and finding that it's the same. So that's what the use of Holoraumy is. It's a strong argument for the equivalence. Oh, by the way, if you've never heard of Holoraumy, let me try to give you one more argument. One that will probably be another thing. Consider SU3. SU3 has a group of generators, let's call them T. The generators give us we can think of these as 1/2 of Gell-Mann matrices. That's the typical way we do it. We calculate the structure constants. You can go to a textbook. Now, take the matrices and calculate the minus complex conjugate of those matrices and call them T tilde. If you do that, you'll find that T tilde actually satisfies the same algebras as the T's. So these 2 sets of matrices, the T's and the T tildes, are both representations of SU3. Now calculate the so-called D coefficients. The D coefficients. The D coefficients are calculated by taking the matrices and not looking at their commutators, but looking at their anti-commutators. You do it on this first representation, you're going to get a D associated with it. You do it on the second representation, you're going to get a D associated with it. And the 2 D's are not the same. You now take the traces of these D coefficients and you find out that appropriate normalization, they look like this. This is what the analog for Holoraumy does in D theory. We're basically looking at what's the analog of D coefficients traced against each other for different representations. So I'm going to end this talk because it's coming up on 5, right? 5 is a good time, right? Or it's a little bit after 5. I'm going to end this talk by throwing sort of a challenge out. So in supersymmetrical physics, in 1979, I was a postdoc at Harvard, and John Schwartz invited me to come to Caltech. And John invited me to come to work on a problem which was called the N=4 Yang-Mills auxiliary field problem, which Melanie is smiling about because this is a problem that's been around forever. And John had seen some of the work I had done at Harvard with Warren Siegel. He thought, this kid knows something. We'll finish this problem off in no time. It was my first visit to the campus of Caltech. And I had a great time. John and I worked our butts off. And by the end of the 6 weeks that I was there, we had not solved the problem. Now, that had always bothered me, that this problem that John thought we should have been able to solve, we were not able to solve. About a year later, 2 of my friends, Warren Siegel and Martin Rochek, wrote a theorem. And the theorem basically said, if you are not too carefully reading it, it says you can't solve the problem that John and I tried to solve. So you have a theorem that says, that's why they failed. Now, the only problem with that point of view is that the theorem, like most physics theorems, includes a set of assumptions. And when physicists typically derive Dogo theorems, and one of the most famous of those is the Coleman-Mandula theorem, which said that you can't have any symmetries with Lorentz spinors in them, which we know is false because supersymmetry is such a symmetry. And the reason the Coleman-Mandula theorem fails is because one of the assumptions in the Coleman-Mandula theorem is relaxed when you talk about supersymmetrical theorems. And so I like to think of physics no-go theorems as actually where-to-go theorems. So if you look at the Siegel-Rocek theorem, one of the assumptions in there is they make an a priori assumption about the form of an action. And then on the basis of that, they derive the theorem. So I've always been curious, what would happen if you drop that assumption? I'm going to show you how to drop that assumption. And it leads to, interestingly enough, a cryptographic problem. So this is the shorthand introduction to the auxiliary field problem. Up here we have what's called the off-shell formation of chiral multiplet. So you can see it's got this F thing that I was showing you about. This is actually a complex version, so this is F plus IG. The equations of motion are here. The equation of motion of F is algebraic. You can use it to eliminate F in terms of m times A. You plug it back in, you see you have a massive complex scalar and a massive biostring. Typical of. And if you try to derive the equation without F, you're perfectly capable of doing it. It comes from this regard. So this thing, the F is the auxiliary field formula. This is the thing that we would like to know in the case of N=4 super-Yang-Mills theory, but nobody knows it. No one has known it for 40 years. And not just it, maybe there's more of them that are necessary. So this is what N=4 super-Yang-Mills looks like when you do this light line reduction. That's the theory I'm showing you. It's got a bunch of bosons, actually 16 of them. So let's do Yang-Mills theory. So that's the transverse components. I'm sorry, let's do Maxwell theory. Transverse Maxwell. It has the scalar pseudo-scalar pairs from 3 chiral multiplets, the auxiliary field from the D multiplet, and then the F and G from 3 chiral multiplets. That's what it would look like in terms of N=1 super multiplets. Here's the action after the reduction. If this was supersymmetry, that is, if I could find a set of transformations on this that would leave it invariant and it was supersymmetry, I would find these three equations here. Let me show you a set of transformations that leave it invariant. They look like that. Now, it's an algebraic nightmare. You got to go off and do the calculations. But you know, you get some coffee in you, and stay up a night or two, and boom, the calculations are done. To show it's true. These transformations leave that action invariant. But the question is, what happens if we calculate DD? That is, take the second D on these calculations and iterate. What you find is that this condition is satisfied, and that's ordinary supersymmetry, by the way. But neither this nor this condition is satisfied. And that's the sign that you don't have what's called an off-shell representation. You have an on-shell representation of supersymmetry. So I've shown you how to take supermultiplets and reduce them to problems with matrices. So what does this problem look like in terms of matrices? Well, it looks like this. This is what the chiral multiplet looks like when you reduce this LR business, these matrices. They become 4 by 2 matrices. Vector multiplet becomes also. And now you want to find the auxiliary fields. You notice in the purely on-shell theory, I only have 2 rows. But to get the off-shell theory, you have to have 4 by 4 matrix. You have to square matrices to be off-shell. That's the lesson. So how do you turn a non-square matrix into a square matrix? Well, one thing you can do is simply introduce a set of parameters that grow the matrix out. And now, how do you make this become supersymmetry? Well, what you do is you say, well, the on-shell theory gives me information about a set of numbers, which I'll call the A's, so boson to fermion transformation laws. The fermion to boson transformation law gives me a set of numbers B. These L parameters I'm using to grow the matrices, and all you have to do is to take this and subject it to these conditions, because these are the conditions that the L's and R's always satisfy in order to define supersymmetry. This looks like a cryptographic problem. The on-shell version of the theory is, so you take these matrices that I'm showing you. Here they are. You take these matrices where the A's and B's are given information, because you know about their values from the on-shell theory. The L's are the parameters you introduce to grow the matrices so that they will be square matrices, because the on-shell matrices aren't necessarily square. And now, you imagine sending a message by a code. And the way the code works is you send the matrices to a friend of yours. And can be open. But in the typical way that a cryptographic program construct works, you send the only partial information. That is, you send these matrices with all the L's set to 0. And you send them to a friend. And now, your friend's challenge is to reconstruct the matrices when the L's are not 0. If your friend knows that it has to satisfy that funny set of algebraic conditions that I show you here, your friend, up to a bunch of plus and minus signs, can reconstruct the matrices you send. It's a cryptographic problem. And so the off-shell supersymmetry problem, which has stumped my field for about 35 to 40 years, is equivalent to a cryptographic problem where the cipher is that this thing is the way that you encode and decode the information. And because cryptography is a well-developed piece of mathematics for various and sundry reasons, I've actually started talking to scientists in government labs. Because I think probably the best cryptographers around are probably there. They're not in academia. And so we are very hopeful that we're going to make advances on this problem that I could not solve with John in the winter of 1979, and that it will come because we will have the advantage of